Okay, so welcome to Instrumental Analytical Chemistry. This is, we're going to be looking at thermal analysis today, which includes things like TGA, which is a thermogravimetric analysis, which is basically a fancy way of saying we measure the weight or the mass of something as we heat it up. We'll also be talking about differential thermal analysis, that's hard to say, and differential scanning calorimetry, which are two different ways to measure the heat flow in a particular system. Okay, so thermal analysis is a way to measure the physical property of something as a function of temperature, and it's generally done on very small sample sizes. So similar to things like atomic spectroscopy, thermal analysis is also generally a destructive technique. Usually you get less of your material back than you did at the start. And for certain techniques, such as thermogravimetric analysis, or TGA for short, you don't get any back at all, because it basically just continuously heats it up until there's nothing left but a sort of a sticky black residue or whatever, the carbon that remains, or the inorganic salts or whatever it happens to be in your sample. So you really need to use small samples, which means that the balances inside of these instruments are insulated from the outside, and they're very sensitive. So you also need to make sure that whenever you're weighing out your sample, that you're weighing it out accurately. So you're talking like maybe like 1 or 2 milligrams, very, very, very small amount. It doesn't really exactly matter. If it doesn't have to be like exactly 2 milligrams or something like that. You just need to know the starting weight. These things are good for studies into crystallinity or crystal changes. So if, for example, you are making some sort of plastic material, or you're making something and you want to know kind of how long it's going to exist for, because some plastics, they start out kind of amorphous, and what that means is there's no real repeating structure. It's not like carbon, hydrogen. It's not like it's not crystalline in nature. Crystalline basically means that there's some sort of repeating structure throughout the entire material. So it goes A, B, C, A, B, C, A, B, C, and so on. But in amorphous, it may go A, B, C, B, A, something like that. Where A and B and C are just different ways of arranging the molecules. So it can be done. And so if you wanted to do that study, you could try to see the long-term stability of your product before, like maybe it starts off amorphous and then becomes crystalline. And then usually if something does that, it typically becomes more brittle as it becomes more crystalline, because the crystals have like a kind of a seam along which you can break it. What else? TGA is useful in trying to find out how much moisture there is in a product, because if you start off with, it's all like a differential sort of scale. So as you reduce the mass, you can sort of say whenever it occurs at different temperatures, what it might have been. So for example, if you were heating something up and around about 100 degrees Celsius, the boiling point of water, you lost 10% mass, then you could postulate that you did in fact have 10% water in your sample, even though you thought it was dry. So here is sort of a go over for that. So thermogravimetric analysis, TGA, is something I've been talking about there. So this is going to measure the weight of the sample as a function of temperature or time, both of which will be scaled linearly. So temperature, it goes up by like 5 degrees Celsius every 5 minutes. So that's 1 degree Celsius per minute. For time, you might just do like, 1 hour, 2 hours, whatever it happens to be. Usually whenever you're doing these sorts of analyses, you want to allow the sample to equilibrate in between changes in temperature, but oftentimes you don't have the time to do that, or there's like a lot of people wanting to use the equipment. So like for example, you want to go increase by 10 degrees, then pause for 1 minute, then increase by another 2 seconds. increase by another 10 degrees, and then wait for 1 minute. That allows the system to equilibrate and allows any sort of processes that might be occurring at that temperature to occur. You're doing this in a controlled atmosphere, so you don't want there to be, usually you don't want it to be a combustible atmosphere. What that means is you don't want things like oxygen in there. You want it to be relatively inert. Usually that inert gas is just nitrogen. It is possible to do kind of combustible TGA, where you change the atmospheric gas inside of the instrument from a non-volatile gas such as nitrogen to a volatile one such as oxygen. And so by doing that, what you could do is you could find out the amount of carbon in the sample, because if you have a high temperature and you have carbon in your sample and you're mixing it with oxygen, what you're likely to get is a fire or a flame. So it'll burn and produce CO2. And so you can find out how much carbon there was in your system. Then sample sizes, again, usually in milligrams or smaller. A sample container is usually platinum or aluminum. It's a very, very small little tray almost, with like a little hook on the top, and you can lift it in using a set of tweezers. So the tweezers are necessary because even because you're working with such small masses, even just kind of the grease from our fingers or something could affect it. I mean, usually you'd be wearing gloves, but still, like, there could be any sort of disruption in the actual weight. So here's a sort of a typical TGA plot. So the blue line is what you would get out from your instrument, and the gray line indicates the temperatures that we are using, and then the time is given as the x-axis. And so the total time for this process was about 30 minutes. So initially you start off with 100% mass. Now that's reasonable because, well, nothing should have happened at low temperatures. So at 100% mass, you're heating it up, and then you get to around about, you get to around about 110 degrees Celsius. So it starts at room temperature, go up to 110 degrees Celsius. At 110 degrees Celsius, you pause for some time. And during this time, some water is lost, about 0.9% of the total mass of the sample. So we can say that water was about 0.9% because that happens around about 100 degrees Celsius. We don't stay at 100 degrees Celsius because and wait, because there can be some barrier to the desorption of that water. So usually that water is fixed to our sample through some interactions between the water and the sample. So the temperature needs to be a little bit higher in order to give that extra energy so that the water can evaporate. If it's kept at 100 degrees Celsius, there's a chance that the energy that we are supplying to the sample is insufficient. Then after that, we start to increase the temperature pretty rapidly up to this final temperature of 950 degrees Celsius. And we see that all of the volatile things have come off. So this could be like an organic material that we're burning or analyzing, sorry. So we lose some weight as the, what do you call this? As the volatiles are burnt off. So this could be things like the product could decompose. It could produce sulfur dioxide. It could produce things like acetic acid. It could produce, it just depends what it is, really, what this volatile thing is. But basically some sort of volatile chemical comes up. And so since you know the initial mass and you know the mass then after that process is completed, then you have this 23.5%. Then we maintain this temperature for some time until all of the volatiles have been removed, and then we reach a point where we change the gas from nitrogen, which is our inert gas. So up until this point, all of the things which have happened to the sample are just internal processes. So there's been no external impetus or external trigger to start any new processes. So we change over the gas from this inert gas to a reactive gas such as oxygen. And then we see that there's a rapid decrease in the mass of the sample. And this is what's known as the fixed carbon. So what we're seeing here is that all of the carbon that's remaining in the sample reacts with the oxygen to form carbon dioxide. And then this is going to lead to this massive drop in in mass, and then what's left at the end is just what's known as the residual mass. So this is like non-volatile compounds like inorganic salts. It could be yeah, basically it's mostly inorganic salts at this point. And so this entire cycle took about 30 minutes. So inside of a TGA, you have a very sensitive analytical balance, which is going to be here inside of the furnace. So this is where we put our sample here, where this B is written here. So our sample goes here inside of the furnace, which is where we're going to heat it up. We have a furnace controls. This is programmable, so we can like change the rate of heating, like how many degrees per minute. We can create pauses so that equilibrations can happen and things like that. Then we have a temperature sensor in there, of course. We have then the rest of this apparatus here, which is going to be our balance. And so this here is part of the balance. So what it's doing is it's seeing the changes in weight. So as this pushes up, because this gets lighter because there's less mass here because the mass was burnt or destroyed, then this will go up, and then this will feed back into this part over here, which will then feed into the electrical circuit. Because what happens here is that this sort of beam, it moves up and down, and it will cut this laser between the 2 points of D. And so what this does is it looks to see how much of the light is actually cut out, so that it can check minuscule changes in masses. And then, so depending on how much of this is cut out, we know whether or not we need to start recording. And so this it's measured in two ways: by this laser being cut in the beam, and by this, which is just a regular balance rate. So then this feeds back into our computerized system, and then we get a readout of some sort, which looks like the one on the previous slide. So it's made up of a sensitive analytical balance with a range up to milligrams. It has a sample holder, which is going to be thermally isolated from the furnace. There's a furnace, which can have temperatures up to 1500 degrees Celsius. Then there's a purge gas system. So that means that we can make use of things like non-reactive gases, nitrogen, argon, helium, etc. And we can have reactive gases such as oxygen and air. Oftentimes you don't, like, most people don't really like it whenever you use reactive gases inside the TGA, because if it's not well enough controlled, it can cause damage to the TGA, because you're burning something inside it, other than what's supposed to be burning. And then the temperature control, obviously the computer. So TGA application, so we look at the decomposition of polymers. So this can help us with quantitative sample mass information, but limited to the decomposition and oxidation reactions of polymers. And so the physical processes, vaporization, sublimation, and desorption. Desorption of things like water. So what we're seeing here in some of these things can be where the polymer initially breaks down into smaller monomer units, and then those monomer units can often be more volatile, and then those monomer units can what do you call this? Can be volatile, and so they can evaporate, be vaporized. So we can see here the 10 milligrams of each one of these polymers, PMA, PVC, LDPE, PTFE, and PI, were heated at 5 degrees Celsius per minute in nitrogen until they reached higher temperatures. You can see that the point at which they start to decompose for each of the polymers. So you can say that PVC is less stable at high temperatures than things like PMMA, LDPE, PTFE. So if you're going to use some of these things for cooking, you'll want the ones which can reach high temperatures and still be stable. So it's just sort of an application of it where you can get it from like a real world kind of process. So here is looking at the polyethylene TGA. So what we have here is the mass percent here on the y-axis, and we have the temperature along the x-axis. And we're heating here at 160 degrees Celsius per minute. So this is a pretty fast heating process. So we're not really going to see any detailed information here, at least not detailed information about things like absorbed water and stuff, because the heating at that speed, we're going to end up going too quickly from our absorbed water to our decomposition to really sort of like say what is water and what is a volatile component. So initially we have the decomposition of the polyethylene. So this can be, as I've said before, the breakdown of the polymer chains and then the formation of the monomer units. And so that will cause a sharp decrease in the mass as those monomer units tend to be much more volatile. They're ethylene units. Ethylene is usually a gas, so those will mostly vaporize. We'll also vaporize any sort of like alkanes or hydrogen gas and things like that, which will evaporate off and leave us behind just like a kind of a charry black residue. This will be the carbon black, literally just carbon. And so we've been doing all of this under a nitrogen atmosphere, and then we wait until there's no real change in the mass, and that indicates to us that all the volatile components have been lost. And then we heat it up, or we continue heating it in oxygen. And this addition of the oxygen gas along with the high temperature means that the carbon will react very quickly with the oxygen to form carbon dioxide. And so then we can figure out, we can confirm, sorry, the mass of carbon in our sample. So we're just burning the ash basically. And this is all the lost CO2. So here is another example. So this is looking at the decomposition of calcium salicylate. So what we're looking at here is just the different processes which are going along here. So we have the calcium salicylate monohydrate here, and then we're burning off the water at 200 degrees Celsius thereabouts, and we're ending up with this calcium salicylate. So basically what we have here are a couple of, or no, this is oxalate, calcium oxalate, sorry, monohydrate. Then we're burnt off the water here between 100 and 200 degrees Celsius. And then we've reached an equilibrium point here where we're just left with calcium oxalate. And then we continue to heat up. And what we see is that we lose a molecule of carbon monoxide. So that's going to we've lost, if we can just look at the sort of the formulas here for the two molecules or the two compounds. We have here calcium, 2 carbons and 4 oxygens. And here we have calcium, 1 carbon and 3 oxygens. So we're missing a carbon and oxygen. So what's happened here is we've volatilized 1 carbon monoxide molecule at this temperature. And then if we continue heating, we've basically totally dried the compound down to its oxide, the calcium oxide, and we've lost a volatilized carbon dioxide this time, and we're left with calcium oxide. Now, how do I know it's calcium dioxide? Well, there's 1 carbon and 3 oxygens here. And then in our final calcium oxide, there's only 1 oxygen. So that means we've lost a carbon and we've lost 2 oxygens. So CO2, most likely carbon dioxide. So these processes are happening at different times. You can see that we equilibrate at different points, and we can see the decomposition process. And so why is this interesting for us? Well, it's interesting because it's a way in which you can kind of model the decomposition of your product. If you want your product to be long lasting, what you can do is you can do this kind of TGA study to try and see as a model, because like obviously you don't know the exact environmental conditions all the time. You don't know how hot it's going to be all the time. It's never really going to be like these sort of temperatures on Earth, at least not at the surface. So what you're doing is you're doing this to try and expedite the process so that you don't have to wait 10 years before you bring your product to market. You can do it within a few weeks if necessary. But this is a pretty good model. There are ISO methods out there on how to predict longevity or product life. We've got this sort of process where it's decomposing in 4 steps until it's definitely no longer your product. But you could do this for other things. You could do this for some of the polymers that we saw earlier. Say you're making a window frame or something like that. You could check to see how your window frame will degrade over time, whether or not it will be suitable for a long service period in whatever application it's being used for. So TGA can give information about second order phase transitions such as vaporization, sublimation, absorption, adsorption, and desorption. Chemical information can also be obtained for phenomena including chemisorption, desolvation, such as for water, decomposition, and solid gas reactions. So these are oxidations or the reduction. So the solid gas one is the carbon reacting with the oxygen to form the CO2. So applications generally in this desolvation, so to see how much water there is in our metal complexes, and to look at the loss of carbon monoxide, which we had here. So these are the reactions which we witnessed on the previous TGA slide. So this was the metal oxalates with the water, losing the water, metal oxalate, losing carbon monoxide to form the carbonate, then the carbonate forming the carbon, or not the carbonate, the calcium carbonate forming the calcium oxide plus CO2. And then if we have a mixture of different components, we can see then when the other decomposition processes occur. So TGA can give information about the composition of the mixture and the relative temperatures of the processes if we analyze the data, for example, using a 2D or a second derivative of the thermogram. So basically this is just this. What we've done is we've taken a second derivative of it. So you can usually do this in different software. So like you can do this even in Excel to take a differential thermogram. And so the reason why we do this is because it gives us the point at which the gradient is sort of like changing. And so we can see an exact peak position of when that temperature is. So like, for example, in this sort of like mass loss, we don't really know what temperature this is occurring at because it's sort of like, do we take it here? Do we take it here? But by taking the second derivative, we can see a very clear peak at 450 degrees Celsius. And so we would say that process is happening at 450 degrees Celsius. And so that's kind of the power of these derivative thermograms. Now you can take a second derivative of a lot of different analyses to try and see exactly where the peak positions are. This just happens to be one of the more common ones. So the 3 peaks here suggest different hydrate stabilities. So we have, we're losing the first hydrate at 140 and then 180 and 205 are different hydrates. And so some of those are stuck on stronger than others. Maybe there are more waters than we think. And so some of them are just stuck on the surface. Some of them are actually almost bonded to the metal complex. So TGA can also give quantitative information about water content. The limit of detection is around about 0.5%. So we can also check sample quality. So if you have a certified example of your new product, such as in this case, oil, you can check to see if it is used oil or it is new oil by taking its TGA. And so the blue line here is a used oil sample and the red line is a new sample. So you can see that they have slightly different decomposition temperatures. So for the used one, it's been degraded slightly. So it is about 5 degrees Celsius, or its decomposition onset is about 5 degrees Celsius earlier than that for the new sample. And then the same goes for the overall stability here in the second derivative differential TGA. We have a difference of about 5 degrees Celsius. So we can really use these TGA's method, or use the TGA method to analyze our product to try and make sure that we can certify that it is in fact what it's supposed to be, that it is in fact pure, because we have, as long as we have a reference material, we can do this. These are just like kind of like the setup for this. So a TGA sample problem, so this is a little bit involved. So a 0.6025 gram sample was dissolved, and the calcium and barium ions were precipitated as calcium oxalate and barium oxalate. The oxalates were treated using TGA, leaving a residue that weighed 0.5713 grams at 320 degrees Celsius to 400 degrees Celsius. This is the oxalate range, and 0.4673 grams in the 580 degrees Celsius to the 620 degrees Celsius carbonate range. And so we're asked to calculate the percent carbon or percent calcium, sorry, and the percent barium in the sample. So just this is what we're doing here is we're looking at the different processes which are occurring during the decomposition. So initially our sample is 0.6025 grams, and it contains calcium and barium ions. These were then precipitated as calcium oxalate, or sorry, barium oxalate and calcium oxalate. So basically we mix some oxalic acid in there, and the oxalic acid reacts with or forms a complex with the barium and the calcium ions, and then they precipitate out of solution. So these oxalates were then collected and they were heated using TGA, leaving a residue of this, which is in the 320 degrees Celsius to the 400 degrees Celsius oxalate range, so somewhere in this range. And then a 0.4673 grams in the 580 degrees Celsius to 620 degrees Celsius carbonate range. And we're asked to calculate the percent calcium and percent barium in the sample. So how do we go about this? So we know that the total combined weight of dry calcium oxalate and dry barium oxalate is 0.5713 grams. We know that because it's weighed here. And we're even told this is the oxalate range. So these are oxalates at this point, but they're dry oxalates. The water has been removed. Then we also know that the weight of calcium carbonate and the weight of barium carbonate is 0.4673 grams. We're told here 0.4673 grams in the carbonate range. We already were told that it's in the carbonate range, so they must be carbonates. So we can then rearrange these equations to express them in terms of what the weight percent of calcium oxalate is and the weight percent of barium oxalate is. So the weight percent of calcium oxalate is going to be equal to the weight of the calcium in the sample times the formula weight of the oxalate all over the formula weight of calcium. And so that means that we can then, so this is the weight of, so this means that we have the weight of calcium in terms of the percentage of the oxalate that is calcium. And so we can divide through the 128.1 by the 40.04, the 40.08 as being equal to 3.196 times the weight of calcium. Then we do the same for the barium so that we get it in terms of weight of barium. So we have really created a bunch of terms here, which are all in terms of the weight of the calcium and the weight of the barium. So we have the weight here of the barium carbonate in terms of barium. We have the weight of the calcium carbonate in terms of calcium. And so we can rearrange these. Imagine this weight calcium is like an X and this weight barium is like a Y in algebra. So we then can in fact substitute this. So, okay, let's look at the carbonate, or sorry, the oxalate example here. So what we have is the weight of calcium oxalate. So the weight of calcium oxalate is here. So that is equal to 3.196 times the weight of calcium. So that becomes this term. Then we can do the same for the barium oxalate. So the weight of barium oxalate, so this part becomes 1.642 times the weight of barium. So we substitute that in. Okay. So that means we have a new equation here in terms of the weight of calcium and the weight of barium in our samples. And then we can do the same for the carbonates so that they become, for example, the weight of calcium carbonate, the weight of calcium carbonate is going to be equal to 2.497 times the weight of calcium. So we just substitute that into our equation. And then we do the same for the barium carbonate so that we now have two equations in terms of similar terms. So say these are X's and these are, I don't know, Y's. Then we can rearrange them so that we can get the value of X. So for example, we would substitute, so rearrange this so that 0.497 times the weight of calcium is equal to 0.4673 minus 1.436 times the weight of barium, and then substitute this into this, and then we will be able to solve for the weight of barium, and then do the same thing in reverse for the weight of calcium, and we get what X and Y are basically equal to. And then the percent of calcium is equal to 0.109 over 0.6025 times 100% is going to be 18.1% calcium. And so we can do the same thing for barium, and we get the percentage of barium is 22.4. So the percentage of calcium is 18.1%, and the percentage of barium is 22.4%. And really all we actually did here was algebra. We were given everything in the question that we needed. And then we just rearranged some things. It looked a little bit crazy because we were using chemical formulas and we're not using X and Y, but it's just really our own personal biases, I think, which caused that sort of confusion. And I mean, even I don't like looking at this so much, but it really is, if we just sort of break it down into X's and Y's, it's much easier. Just make sure at the end that you report the answer in terms of the percent calcium and percent barium at this instance. Okay, so that's a TGA example of like maybe something you might have to do. So DTA, differential thermal analysis. So this is looking at sort of the heat flow through, or sorry, the temperature thermal flow through a sample. So instead of heating something up until it sort of decomposes, well, we can do that as well, but usually people don't like that because DSC or DTA instruments are usually pretty expensive, and they're usually hard to clean, and that's time consuming, and it means other people can't use it. So it's better to run a TGA first and just like totally blast your sample to see what temperature it decomposes at, and then just avoid reaching that temperature. The glass transition here. So we have, this is kind of a change in the material where it goes from like an amorphous type material to a glassy type material. We can see crystallization points, we can see melting points, so that's usually an endothermic process. Crystallization is an exothermic process, so heat is released. Endothermic melting, that's going to be heat is absorbed. Then oxidation reactions, no oxidation would be this line happening here. So DTA gives qualitative information about the phase changes of a substance by comparing temperature changes with a reference. This is more reproducible in capillary or hot stage methods. The most common version of this is DSC, which is differential scanning calorimetry, which looks at sort of heat flow through the sample. So how this kind of works. So if we have power compensated DSC, we have two samples. We have one, we have two chambers. So we've got chamber for our sample and chamber for our reference. And so we're going to be looking at the heat flow through the system and comparing the sample to the reference. So DSC gives quantitative information about the phase changes of a substance by comparing energy or heat flow differences with a reference. And then power compensated DSC is less sensitive than heat compensated DSC, but has faster response time. And so it's thus ideally suited for kinetic studies and capable of higher resolution than heat compensated DSC. So here we have this part here, which is sort of a thermocouple attached to our sample chamber. So measures the difference between programmed and actual temperature. The power is adjusted to compensate, and this energy is the DSC output. So this is power compensated DSC, which is a very high response rate. So that's because it's using electricity. Electricity flows very quickly. So it's less accurate than heat compensated. But if we're trying to study the kinetics of something, so like the speed at which a process occurs, then power compensated is better because it has that faster response time, which is what we're looking for and what we need in order to make sure that we have accurate kinetic information. So the power compensated DSC, so the temperatures of the sample and reference are equal and increased linearly. So we increase the temperature by 1 degree Celsius per minute, and we measure how much energy is required to continue heating at 1 degree Celsius per minute. Now, obviously, the reference material has a known response, and so because of that, we're very much aware of like its properties, so it will continue to linearly increase in temperature at the same amount of power generally. But the sample may not. The sample may go through things like crystallization processes, may go through things like melting, it may go through some decomposition of some sort. And so the energy required is not only the energy required to heat up the sample, but it's also the energy that's used or given out by those different processes. And so the sample and reference are heated with separate heaters. So yeah, these heaters are separated from each other. They're isolated from each other, but their relative amount of energy required or electricity required to heat them up is, of course, measured. So the different components in a power compensated DSC. So we use a platinum resistance thermometer. So this is more precise, better linearity in a wide temperature range. We have separate furnaces or cells for sample and the reference. It's capable of rapid cooling, heating, and equilibration of temperature due to the design of small size of the furnaces. So because they're small, they don't require a lot of energy to heat up. Platinum resistance thermometers are in contact with the sample and reference holders, and these sense the difference between the programmed and actual temperature. So this is the error signal. So the error signal is used to adjust the power applied to the sample or to the reference platinum resistance heaters, and the DSC output signal is the difference in the power required between the sample and the reference so that both equal the programmed temperature. Yeah, so sometimes we have to reduce the amount of power that's being given in during a melting or during a crystallization process, because the crystallization process produces heat, and so that heats the system up. So if we continue to add the same amount of energy, the system's temperature will increase too rapidly. Differential scanning calorimetry. So if we look at heat flux DSC, we have an example of a heat flux DSC over here, where we have our two samples inside of the same instrument. We have then the different gas purge inlets. The reference pan is here, sample pan is here. It's all resting on a thermoelectric disc which is made of constant tan. So this is an alloy of 60% copper and 40% nickel. Then we have the thermocouple junctions. This is the thermocouple between the wire here, which is going to be used to transfer the heat, and the actual reference pan and the sample pan. So then the heating block here, these are made from alumel and chromel. So it says down here what chromel is and alumel is. They're just alloys of nickel, aluminum, and sometimes chromium, sometimes iron. They're used because they have well-known heating properties. So in heat flux DSC, the difference in heat flow into the sample and reference is measured while the sample temperature is changed at a constant rate. Both sample and reference are heated by a single heating unit, and heat flows into both the sample and reference material via an electrically heated constant thermoelectric disc, which is over here. Here's the thermoelectric disc. So the small aluminum sample and the reference pans sit on raised platforms on the constant disc. Heat is transferred through the discs and up into the material via the two pans. Differential heat flow to the sample and reference is monitored by chromel constant thermocouples formed by the junction between the constant platform and chromel discs attached to the underside of the platforms. So we have here the constant disc, which is where the heat is going to flow through the junction into the sample. So here we have it again. So the sample and reference material are heated by the same heater in such a way that the difference in heat flow into the sample and the reference is measured as the sample temperature is increased or decreased linearly. So in the power compensated, we were measuring electricity. Here we're measuring the difference in the amount of heat. So chromel constant disc thermocouples measure the temperature difference between sample and reference, and heat flux is then calculated from the temperature difference by this equation, where the delta H, the change in heat, is equal to K delta T. K is calibration constant for your system, and delta T is obviously the change in temperature. So DSC, so we can look at different thermal events. So here, so usually a peak, which is positive, at least compared to the baseline, is going to be due to an exothermic event. And then any negative peaks or troughs are going to be endothermic events. So here we have our glass transition temperature, which is a change in the material from a kind of amorphous type material to a glassy type material. And so these heat flows are due to different kinetic events. So the exothermic event may be crystallization, and the endothermic event may be melting. So experimentally in DSC, we have a sample pan, which is usually made from aluminium, but other materials can be used if we need to go to very high temperatures, because aluminium melts at 650 degrees Celsius. The sample is, of course, weighed and sealed with a little cover, also made from aluminium usually. Purge gases are nitrogen or helium, just to make sure that there's no combustible processes happening. Then to do the calibration, we look at the baseline and subtract. So that's done without any pans in the instrument. And then the heat flow calibration is usually done with indium, and heat capacity calibration is usually done with sapphire. So one of the applications of DSC is looking at the crystallinity of a particular polymer. So this is maybe something, if you're in the polymer industry, that you might use to see like how much of my material is actually crystalline. So the crystal fractionality of a polymer can be determined by comparing the fully crystalline material. So if we look at the fractional crystallinity, it's going to be equal to the heat flow change of the sample over the heat flow change of the crystal. So we can see here that in this crystallinity DSC heat flow, we have an onset transition here where we have the glass transition. So that usually occurs before we have any sort of crystallization processes. Then we have the onset temperature, which is between here and here. That just means that the event is starting to happen. It hasn't happened yet, and it happens usually very sharply. Usually the crystallization happens very quickly, and the onset of the event is usually here, where we draw the gradient through the steepest point. So we get the tangent of this line, and then we draw it down to what would be the baseline, and we find out that point there is going to be the onset of our crystallization event. Okay. Then finally, the DSC application. So the determination of transition temperatures. So for example, glass transitions, melting points, crystallization points, and the associated energies with those, because remember that these heat flows are in milliwatts. So that can be translated into energy. What is a form of energy, I suppose. Glass transition temperatures, TG. These are especially important for the characterization of polymers. The material undergoes a phase change from a glassy to rubbery state. At the TG, the polymer undergoes changes in volume and expansion, heat flow, and heat capacity. And so this is an application of DSC. So this is really quite useful if, like, for example, your polymer goes through a glass transition during a regular working day. So like what I mean by that is like maybe the glass transition is somewhere around about 30 degrees Celsius. Well, during the day, maybe temperatures exceed 30 degrees Celsius. But then at night, maybe they drop down to about 25 degrees Celsius. So it's passing through its glass transition temperature every single day. So is this going to have some sort of an effect on my product lifespan? Is it going to maybe cause changes in it? So you can do this not only just for polymers, like polymers in the sense of like hard plastics, but it can also be done for cosmetics and things like that. And like, you know, those sorts of physical changes can have chemical changes down the road, and so it can affect, like, you know, sort of the safety and the longevity of your product. Kinetic studies, then isothermal experiments, so it can check the crystallinity and crystallization rates, look at reaction kinetics, and then finally a determination of purity of compounds by measuring the melting temperature. Okay, that's thermal analysis pretty much in a nutshell. Not a huge amount of detail and everything, but hopefully I gave you some idea of the different applications that are possible.